let's talk a little bit about what it looks like to actually build it and how you might go about building. So there's a 12-step plan that I'll discuss right here. And this is the kind of approach that we've been using many times now with a variety of customers. And so first we start up with the priority area. So in other words, someone may say, you know what, my subledger isn't working well. Users are complaining about that. So let's go ahead and find that. What we really want to try and do is make sure our scope isn't too great. We're not trying to solve every performance problem in this first go-around. Let's pick a star. Let's pick a fact and optimize that. Next thing we've got to do is find some common use cases. So in other words, let's identify 10 to 20 reports that are indicative of the kind of usage that this fact table and this star might actually see. We're not looking for outliers. We're looking for common use cases. So identify, a report that may come in with no prompts filled in, because that's the way the report starts off, but also find one where that has a couple of common values in the prompt selected, so a little more reasonable scenario. Don't forget about data security. That impacts performance. Any filtering you have on a user or a group or a role, you want to make sure that's included as well, so we get a complete, accurate picture. Okay. Then we start, OBI can generate the actual SQL. We want to take a look at it. We're going to start looking at that SQL, and this is where some strong SQL skills and tuning skills start to come in. We're going to look at it. And the very first thing we're going to do is see if, hey, is there some low-hanging fruit that's missing on our source, on our primary data model? Maybe partitioning isn't set up. Maybe there's some missing indexes. And so if we can do that, we can do that relatively quickly, and that may, if we're lucky, solve our problem. We don't need to go through any of the additional steps. However, the reality is, in many cases, those are either in good shape or it's not enough. So we actually have to start some work on building a performance layer. So what we'll actually do is we'll start to prototype a new data model to match those needs. And this is, again, more SQL handcrafting. This is where we're going to create some new tables. We'll look at the SQL, say what fields are being used, what filters, what calculations, et cetera. What might be a perfect solution to make a very easy and fast SQL. And so when we build these new tables, we go ahead and we adjust the SQL to use the new tables, right? We have to rewrite that SQL by hand, and we'll rerun it. Okay? If it's not good enough, we go back to step 5 and we'll repeat. If it is good enough, if we've made substantial improvements, we say, okay, let's go ahead and put this into OBI so that we can actually see how the report works. So we'll go ahead and we'll map it into OBI, and we'll do a quick unit/regression test to make sure the results are the same. We don't necessarily need to map every single field in or every single metric. We just want to get the basics here to make sure that our structure is in good shape. And so then we go and we benchmark the actual report using these prototype tables. Keep in mind that a typical report will have many SQLs in it. So although you may have tuned one SQL, well, what does it look like when 6 SQLs are actually issued? And so now we get a truer perspective of before performance and then new performance. Okay? Assuming that's all good and we're done, that's kind of where the prototyping leaves off, or the design, if you will, and we hand it over to the actual development team to go ahead and implement. So this is where you actually build it in your ETL tool, which would be Informatica and the DAC. Right? And we go ahead and we complete out the Oracle BI mapping. In other words, making sure all of the fields are properly mapped in. Okay? We do a formal regression test. Luckily, regression tests are relatively straightforward to do, assuming you have the environment. And we go ahead and we deploy it, and then next thing you know, you're going to feel great because your users are astonished by the performance improvements you've achieved. Talk a little bit about our philosophy here. Now we're getting into some more of the technical areas, right? So I/O is a killer. We want to reduce I/O with extreme prejudice. We need to find ways of killing it and eliminating it at wherever it happens to be. And so, as I said, we want to see if we can do some work on the BIS model. Could be a very quick win for you. Right? We want to do all those techniques that we would normally do in database tuning: partition elimination, compression, indexes, aggregates, star transformation. These are all things that are going to go into the performance layer. We want to let the performance layer do the work, not the report query. So this is the build it and make it happen overnight. So build it once as opposed to having it built in the query time every single time. We want our queries to be very simple with very low amounts of logic in them. The more the database has to do at query time, the slower it's going to be. We want to follow the KISS principle, which is keep it simple, stupid. Right? We want a very simple and clean star. We do not want snowflake models. Snowflakes are bad for performance if they have any amount of size on them. The database optimizer will get confused. It simply will. Okay? We want to ensure that OBI is mapped properly and uses correct tables with perfect SQL. I'm a firm believer that when you're building your repository and you're building reports, it's absolutely mandatory that you not only look at the SQL, you need to know what it should be. And if it's not what it should be, the SQL is not correct. If the SQL is not correct, it's not optimal. If it's not optimal, it's not going to perform as well as it should. So we want to generate perfect SQL out of OBI, whether it's using our base tables or whether it's using our new performance layer tables. Right? We also want to focus on a general approach, right? Go with the rising tide, lift all boats. I don't want to build one table for every report. That's not a scalable solution. You're going to find yourselves kind of wallowing in overload with too many tables, and it's not going to work out for you. So if we can find a set of tables that works for, if one aggregate table can work for 20 reports, fantastic. That's the kind of solution we're looking for. Okay, let's start getting into it now. Four basic kinds of tables in the performance layer, and we'll go over all of these in more detail in the next few slides. Skinny dimensions and fact tables. This may be a concept that you're not familiar with, and this is particularly useful for the BI apps, or when, in some cases, I've seen data warehouses with very, very large and wide tables. So we're going to make a skinny table so we can travel light. We may need to pre-build some logic and build a new dimension table. Sometimes folks will say, oh, you know what, I'll just do it with a big case statement. Well, that's not very good for performance. A mini dimension table, another new concept for many folks. This is a unique idea where we're actually taking key fields out of a dimension and we're getting a distinct combination of them to make a very tiny table. It only has a few fields in it, and it's a fantastic way of linking in, particularly with aggregate tables, number 4. Those are our normal standard aggregate tables that are pretty common in the industry. We're going to build these directly from the base BI apps or data warehouse tables. And our goal is to use these as many places as we possibly can. There will be some cases where you probably don't want to bother optimizing. For example, it's a very common pattern that you start very summarized and you drill down, you navigate, and eventually you end up on a list report. Well, list reports are really not necessarily what we're focusing on here, although some of the principles and things you build in here will actually help your list reports. Some guiding principles, right? The application use cases drive the layers design. We've mentioned that before. All these things we mentioned before. Minimal data for the job at hand. We want to aggregate fact data where needed. Denormalize. Denormalization is a key tenet of dimensional modeling. Joins are expensive, joins are slow, and they confuse the optimizer. We want to pre-build calculations to eliminate extra joins. Right? If there's a way we can do that, let's do that. And we want to pre-split data sets based on logical usage. Sometimes too much data is thrown together into one big table for simplicity's sake. Well, in reality, it's actually used. They're separating it out at query time. And so that's a design consideration that we want to undo in the performance layer. Just a quick refresher here on the basics of partitioning and indexing, and this is what you would want to ensure is happening on your base data model. Right? We want to make sure all of our fact tables are partitioned if they're of reasonable size. Typically, it's on months. Right? This is where the database can simply eliminate a large portion of the data set, and it allows for nice, small local indexes, which are faster. On the indexing side, the key thing is on our fact tables, all foreign keys, in other words, our underscore with columns, should have single column local bitmap indexes. That's mandatory. You should always have that. We want to have single column bitmap indexes on dimensional fields where we're doing lookup. So anything that's in a prompt or a filter, we want to actually put a single column bitmap index. There's a couple of special cases here where snowflake models exist where you need a complex composite index, but generally that's not the case. And then sometimes for list reports, we may make actually be a large B-tree index for join backs to large tables when we're getting a lot of data fields. Okay. Skinny tables, highly selective versions of the BI apps tables. Kind of think of it as horizontal aggregation. In other words, if I have 100 columns in my base table, I'm only actually using 10. So I'm going to make a new version of that base table, okay, that only has those 10 columns in it. And it's valid for both dimensions and facts. We have skinny dimensions and skinny facts. Very simple to build. In the next couple slides, I'll show you what that looks like. Our goal here, why do these exist? Our goal is to reduce our average row length. Right? If we can cut that table down to 1/5 of its original size or 1/20th of the original size, we've now substantially improved our I/O. And I/O is our main thing that we're trying to eliminate. Right? Be careful. We don't want to put too much stuff in these tables, only the things we need. For example, an address, you probably are never going to use that in your actual dashboard. And if you do, it's going to be more of a list report or an exception case. Right? And the BI apps metadata columns, such as integration ID and data source num, don't bother bringing those things over. We want to keep this thing very, very lightweight. A key thing about skinny tables at the bottom is that the row sets are identical. They're one-to-one with their base tables. So if there's 1 million rows in the base table, there's 1 million rows in the skinny table. Now the great thing about that is we can simply reuse those row widths. Any of those new surrogate keys that we've created when we've loaded our base table, we simply reuse them. And that actually works out very well for us because we can configure OBI to use either the base table or the skinny table with very little effort. It'll link into any existing fact tables because it has the same row width. You don't have to change anything. So here's what the creation process for a skinny table looks like. This happens to be a fact table. and this is from the account budget fact table, right? And so we typically, when we're prototyping them or when you actually end up building them, you either do a CTAS operation, you can do an insert append, or you can use materialized views. I typically don't worry too much about which technique you use. There's pros and cons to each. Some customers feel more comfortable with others, but they all effectively do the exact same thing, right? So what do? Over on the SQL, we create the table, we compress it, okay? Since we are basically rebuilding this table every single time we go through it, we're going to compress it. Compression is something we should be using heavily in our performance layer. In fact, every table should have compression on it. Compression in the database level is just like a zip file. It can actually give you a very nice benefit. And again, it cuts down I/O is why we do it. If we need to, we build our table in parallel to make it build faster, right? And so there'll be a little bit of tuning based off of your hardware environment as to what number you actually throw in there. Then in blue, we partition it. This particular one is partitioned by range, so it's done on a monthly basis. Okay, whatever partitioning scheme we have in our base table, typically we will use the exact same scheme over in our skinny table, right? And then we do a select. Again, we have our parallel statement. We select all the fields that we want, right? We even go ahead in yellow and do some logic, right? If it makes sense to do the logic, we don't want to overdo it, okay? And we have a join in there and all that's equal. So this will go ahead and make a table with the same number of records as the base table, but it will use, as you see, it only has 6 columns in it as opposed to perhaps 100. It's going to be much faster. Don't be afraid. The database is very fast at these kind of operations. You would be surprised. For 100 million rows, it will only take a couple of minutes to build it. And I'm not talking 15 minutes. I'm talking like 2 or 3. Databases are very fast at this operation. Okay? We can enhance these tables with additional logic where it makes sense. If we can eliminate a join, then do so. If it's just a very simple A plus B, then don't bother doing that. That doesn't make sense to do that. In the bottom, I mentioned data set splitting before. This is something from the HR analytics where events, an actual event, in other words, someone gets hired or fired, is also in there with monthly snapshots or of headcount. So in the RPD, they're actually used differently. They're filtered, 2 separate filters on them. And so we can actually split those out into 2 separate tables. The events table turns out to be only 10% of the overall table. We've just given ourselves a huge benefit by not having to factor in all those snapshot records when we're looking at events. So some real-world examples, right? It is very typical to get 10, 20, even 50% I/O benefit in the skinny fact versus the base fact. And this, again, our goal is to reduce our average row length. We use compression, record set splitting, and again, this is no aggregation. Okay? And you see some of the examples over there on the right. These are real-world examples. Anywhere you see they're from 11 up to 56 times of an I/O benefit. So that means that the workforce events was only 1/56th the size of the original table, which is a huge benefit. Dimensions also have benefits, right? We want to make sure we do those as well. Denormalization is part of this. We have an opportunity to eliminate our snowflakes and even some outer joins. So a few examples there. Just swapping out 2 very wide dimensions and replacing them with 2 skinny dimensions, not touching the base fact table at all, we got a 6-fold query improvement, query performance improvement. Another one, 11 seconds down to 4 seconds with 1 skinny dimension. These are very simple to build, very easy to model. So you can get some very nice benefits with these skinny tables. Pre-building common and complex calculations. A very common problem is people rely too much on the repository and the query to do the work. Let's pre-build some of that work. So first example that's very common is binning and bucketing. If you see there in blue, case when, and there's a range that's done on order amount, and we put an actual text value of 0 to 100. Well, pre-build that into a table. If you're familiar with the BI apps and configuration files, this is done like crazy everywhere. But if you have new requirements, please follow the same approach and build those into their own small table and create a new key for them and link them in. That way the database does not have to process all this logic at query time. Another one I see is date formats. Perhaps you don't like the date format that comes in your period table, your day table. Well, build your own column that has exactly what you want instead of doing all this query time logic. It'll be a huge benefit for you. It'll be much less error prone as well. Mini dimensions, another object in here. This is simply a higher set of levels of a larger dimension. It's a combination of a few different Kimball dimensional modeling concepts. But the point is that we're going to take a distinct set of our key fields from a large dimension table. So let's look at the query on the right. We'll create a table, WC employee mini dimension, compress as always. We always want to compress. We're going to end up building a new table with a much smaller data set. So that means it's not one-to-one with the base, which means we need a new row width, a new surrogate key. And so this particular query here actually selects 5 different fields from the base employee table. And those are the key fields that we actually were using in our dashboard. There's lots of other fields, but they were not critical for the dashboard environment. These were various prompts and column selectors that we had. And so we built this table, and we actually went from 9 million rows down to 5,400 rows in this table. Think about that for a moment. That's a phenomenal benefit for actual performance. Okay? The visual here shows you how these things actually kind of link together. So how do we use these? Right? We can use the mini dimension table in 2 different places in our performance layer. We can link into skinny facts. Right? So we have a separate foreign key in addition to the base foreign key. So in other words, we in our skinny fact table, we might have employee WID and employee mini dimension WID. We can have both of them. And what we'll do is we will let OBI figure out which is the best one to use based off of the query. We give OBI that flexibility. That's what OBI is fantastic at doing. So let's let OBI figure it out for us. Okay? And so now our skinny fact has the option of joining to this new mini dimension table, which is in green. It has the new skinny dimension table, right, which is in kind of the brownish red there. And then as a backup plan, we haven't taken anything away. We've eliminated 0 configuration. All the original stuff is still there. We can still link into the big, huge base dimension table, right? And so the visual there shows you the differences between the 3 kinds of tables and what you're going after. Another benefit of these mini dimensions is now, since we have a very small set of commonly used fields, we can go ahead and build an aggregate table at a very high level, right, very top of the data pyramid. And so instead of just building it off of customer region, we may actually be able to build it off of several different customer fields. So we get a lot of inclusion of our different fields that we're going to use while still maintaining fantastic compression ratios and aggregation ratios. Right? And if we do this correctly, if we analyze things properly, mini dimension and our skinny fact and skinny aggregates can serve a very large percentage of your dashboard queries. The goal is to lift the workload off of the base tables onto this performance layer. Right? A couple more examples here. This is mini dimensions and fact aggregates. These are real-world examples. Went from a report that timed out after 10 minutes to just 4 seconds, okay, on very large data sets. Okay? These offer fantastic benefits. Okay, aggregates, I don't want to spend too much time on here. I don't really have too much to add about aggregates. All the standard kinds of things in a fact aggregate. Aggregates are not necessarily, you know, the cure-all weapon. Aggregates do nothing for detailed and very highly filtered reports. They are great for summarized reports. That's when you use an aggregate. Okay? Typically, we want to do about a 10-to-1 ratio. We want to use all of our tools that are available to us in the database. The database is designed. Databases know about data warehousing and BI queries. Let's use the features that they've added for us. Okay? So a little bit of summary here about building it. Right? It's relatively simple. Okay? But you do need a strong SQL and tuning expertise. You need to have someone who has some experience doing this, who knows how to look at a query and can break it down and say, you know what, I actually need this table. Well, when it actually comes to building them, it's actually pretty simple. We want to look at actual use cases. What is our dashboard and report and RPD configuration set up to be? How are people using the dashboard? What prompts are there? We want to make sure all of our I/O, we focus on all of it. And so that's where something like a skinny dimension table. It doesn't reduce the number of rows, but it can cut down your overall I/O. Remember, we're always in a multi-user environment. If I cut down my I/O, it's going to help your query out. Right? And if you've got lots of users hitting it, that's an overall I/O load that we're going to reduce, which is critical for performance. And of course, we want to use all of our database tools.